Hello, everyone. So today we're finishing up really the end of the kind of data section, and we're finishing up with something that's actually quite important. It's the idea of analog versus digital. Now, why this is important is this kind of comes to the fundamentals of kind of the way computers interact with the real world, because the real world, for its most part, is analog. Okay, whereas the digital world, okay, so the computers tend to be digital. So I'll explain the two kind of concepts and what they really mean, and then you'll see for yourself. So if you remember the last video, we were talking about pixels and how pixels represent bits, and those bits represent, and pixels represent colors, and the amount of pixels represent the depth of the resolution and the richness of the color and all that type of jazz. Okay, so I'm going to try and explain digital and analog in the terms of sound, because we've done it already in terms of colors and pictures. It makes more sense just to kind of tidy this all up. So this is a graph, okay? And this is time going that way, okay? And this is what's called amplitude. And here is a sound wave, okay? Or a light wave or whatever you want, but it's a wave, okay? And as you can see, this wave is continuous. When I drew it, I did not take my marker off the page at any point, so it's a continuous line. Now, you would have come across the word continuous before when you were doing types of data for statistics. You had this two types, continuous and discrete. And continuous data, you could always find, for example, continuous data was height or time or something like weight or speed. You could always pick any two heights and find another height in between them. It was continuous, whereas discrete was shoe size. There's only a certain amount of shoe sizes. If you use the English system, you're a size 8, size 8.5, size 9. You know what I mean? So there's no 8 and 2.948 of a shoe, okay? If we use the European system, I think it just goes up in single numbers, 42, 43, 44, 35, you know what I mean? But they're discrete, okay? So it's the same idea with analog and digital. With analog, you have the continuous set of data points, where if you pick any two data points, you will find another one somewhere in between it. With digital, you don't. Okay, so to put this into context, if this was a song that I want to listen to, it's an analog. The amplitude, the height of each crest and the depth of each trough of the wave that makes the sound is determined by a point. And unfortunately, there is an infinite amount of points. Digital, and I'll show it to you in a different color, just so you can get the kind of clarity on this one that you're probably going to need. Digital, unfortunately, can only take samples and treat them as a 1 or a 0, high or low, whatever. Okay, it can only take samples. So the continuous analog, in this case sound wave, it's one continuous piece of data which keeps changing. It's never the same at any point to another, because even though you might think that they're the same height, time has changed, so the coordinate would have changed. Okay, to convert the analog recording to digital data, we need to take samples of the heights. And then recreate it. and recreate it like that, where each one is a 1 and the gaps between it are zeros. Okay? So obviously the amplitude can only take a certain value. The height can only take a certain value depending on what's called the bit rate. And that's the rate at which you sample the analog signal. So obviously once you've done this enough times, you will build up close enough approximation to the original. And the higher the bit rate, the more accurate it will become. You know, instead of having this big jump here, you might have a smaller little, you know, you might half that and have another little bit, and it'll get better and it'll get better and get closer. So you could imagine having, if you had a high enough bit rate, you would have a high enough amount of infinitely small rectangulars that could approximate the curve under which they're living. So you can see this one kind of, look, if I start here, it's pretty good at doing it, but it's not exactly accurate. Look at these little gaps here. You're basically estimating that between there and there, it's not really touching that one. You know, you're all these gaps. See, I'll put them in a different color. Give me a green. Okay, see these little gaps here? That's missing information in the digital sample that's not missing in this sample. Why is it not missing in this sample? Because each coordinate that creates this infinite continuous wave is accounted for. Whereas here we're estimating between one coordinate and the other that the curve will continue in that upward direction. And similarly, if you have that one sampled and this one sampled, you're assuming that the curve jumps down here. And it doesn't go kind of all widdly before it goes down. Okay, so that's the idea. The digital data is about the same shape as the analog data, but it's not continuous. And that's the important thing. It's just not continuous. There's lost data. Okay, so when we're sampling digital sound, we sample it in the millisecond range, not the second range, in order to increase the bit rate and get less loss of the original quality. But the quality is never the same. And that's why a lot of purists prefer original vinyl over digital. Because when you're creating music and it's been transferred to a vinyl record, the needle is a lot more sensitive and is continuous. So it will pick up a lot more of the individual intonations and peaks and troughs than a sampling system will. Now, AI is beginning to account for these gaps and work out algorithms to fill these gaps. But the reality is it is not perfect. It can never be perfect. Okay? So, for example, the sample, as you widen the gaps and take less samples, it's going to increase it. And then how frequently you take those samples. For example, frequency is measured in kilohertz. It's the number of cycles that'll pass a given point. That's one cycle from there to there again. If I put my finger there, then how many of these pass there in a second is the hertz, the rate at which it's passing. And obviously, the more samples you take per hertz, the more likely you are to pick up those tiny inflections or those tiny little missing pieces of the puzzle as you go along. Okay? Bit rate itself, the formula for it, just so you know, is the frequency multiplied by the size of the sample. Okay, so it's a simple enough formula. So if you know the size of the sample in bits, frequency in hertz. Okay, increasing the sample frequency means that the analog recording is sampled more often, and obviously if you do that, you get better quality. It'll be more like the original. Okay. Also increasing the sample size, means it picks up quieter sounds, even if they're happening at the same time as louder sounds, because you have more to work with in terms of. So, for example, let's take two imaginary data blocks. Okay, so this one contains 1,000 bits, and this one contains 1,000,000 bits. Even if I have the same speed, I'll catch more things in 1,000 bits or 1,000,000 bits of information. Sorry, million, than I will in 1,000 bits of information. Even if they're both being read at the same speed. So the bigger the sample size, the faster the frequency, the more you'll pick up on more of the information. Okay, it just makes kind of sense. Okay, however, and this comes back to where the larger the sample size, that means the larger the file, the more cumbersome it's going to become, and that comes into our whole area of data compression and all that type of stuff. So why I'm dealing with this through sound, because it's an easy kind of way to for you to be accessible to it. But this is a fundamental issue with computer science. Everything we do in the real world, everything that we'd like, sorry, not say everything, a lot of the things we now want computers to do means that we have to find smarter ways of converting our analog signals into digital. Now, it's not too hard. For example, the microbit that we use, we can put, it will sample, for example, the temperature maybe 1,000 times a second. So when you get the temperature reading from your microbit, it's not truly the temperature, it's the temperature as best it can sample it at a given second. Okay, so it is what it is. It can only do so much because it is a computer after all. It's a very simple machine. It can only do so much. Okay, we have converters that do convert the analog signals into digital. Okay, now not everything we do is analog. For example, a switch is a digital input. It's an on and off. It only has two states. Okay, there's a lot of systems that we use that only work with a digital input. For example, a lot of sensors that are used to either start or stop machines will do so based on a simple input output. Okay, so it's a 1 or a 0 that'll start or stop the circuit. If a temperature, let's say a sensor in a house is meant to turn on the heating when it gets below 5 degrees. So, the sensor might be an analog to digital sensor. So it's reading the analog temperature and converting it to digital. And then when the digital reaches a certain number, it goes on. So you have ideas like that. But I thought it's very important to kind of talk about the analog digital world because, it is one that you will come across. And you could be asked to define it. So that's a nice way of defining it. I would define analog as being continuous data, whereas digital is data that can be expressed in the forms of discrete 1s or 0s. Okay, thank you very much. Goodbye.